Hey, have you checked into your sink lately? There's a slight chance that you might actually have a leak under there. Speaking of leaks, problem 68 describes a water tank with a height of h and a small hole at the height y. Water is replenished to keep h from changing, and the water squirting from the hole has a range of x. This range approaches 0 as y approaches 0 because the water squirts right into the ground, and the range also approaches 0 as y approaches h because the horizontal velocity also becomes 0. Thus, there must be some height y between O and h for which the range is maximum. Let's talk about that. Part A asks us to find an algebraic expression for the flow speed v which the water exits the hole at height y. Despite the vague question, the answer is quite simple and easy to solve for. First, we look at Bernoulli's principle, which states that P1 plus 1/2 rho V1 squared plus rho GH is equal to P2 plus 1/2 rho V2 squared plus rho GH. These H's, P's, and V's are all different depending on the object. However, the important part is that they're equal. We can actually substitute H1 and H2 for H and Y, P1 and P2 for pressure of the atmosphere, and V1 for 0. Taking all that into account, we get an equation like this, and simplifying further and solving for V2, we get V2 is equal to the square root of 2g quantity h minus y. And that's actually our final answer. This equation actually makes quite a bit of sense looking at it. Although it seems a bit complex, it's actually quite simple to understand. By breaking it up into variables and constants, we can see that 2g and h are our constants, while v2 and y are our variables. Knowing this, the smaller y gets, aka the larger difference between h and y, v2 will increase. This makes sense as the problem stated that as y approached h, the velocity would approach 0, meaning that at the bottom it would have the fastest speed. Some of you may be asking, where's part B? Well, lucky for us, Professor Tornado said that we could skip part B and gave us the answers. God bless you, Tornado. All praise the almighty blobfish, may his spirit rest in me. But now, let's get on to C. C asks you to combine your expressions for part A and B, then find the maximum range x and the height of y. Well, looking at this, it's a simple min-max problem from calculus. If you guys haven't taken Math 10A, 10B, or calculus in high school, I'll go through it really quickly with you. What we need to do is take the derivative of the equations that we found in part A and part B. A derivative is basically the instantaneous rate of change of a function, our function being the two combined equations. Part B gives us equations t is equal to the square root of 2y over g and x is equal to v square root of 2y over g. Combining these two equations with the first equation that we have, we get an equation of x is equal to the square root of 4y times the quantity h minus y. This equation works as our function, so we can take the derivative of it. The algebra here is actually pretty complicated with exponents and multiple cancels in variables, so make sure you're just checking your work every step of the way. Taking the derivative with respect to y and solving for y, we end up getting an answer of y is equal to h over 2. This is the height of our hole, and it actually makes quite a bit of sense looking back at the problem. The problem stated as y approached h, the speed would approach 0, but as y approached 0, the range would approach 0. So to get the maximum range theoretically, it would mean that y would have to be in the middle between h and 0 or h over 2. The second part of part C is a bit harder to explain, so I'll let the math explain it for us. Plugging in h over 2 for y and solving for x, we obtain the answer x is equal to h, meaning that the maximum possible range for our water would be the height of the container itself. Some of you may be thinking, what's the point of solving for an equation if we can't find a tangible answer? Well, every equation has its use. In fact, I even used the equation found in part A on our lab this week. So I hope you can use that on your lab this week as well. Anyway, that's all for me for now. Thank you for watching.